recording. Here we go.
I think Alex has already seen this anyway.
Yeah.
She's inside the tent.
It says recording. All right. So I think you guys have got some slides to show. So that's probably the entry point here. So is it Louis or Ben? Take it away.
Yeah, I can probably start rattling off some brief things about dLux. So yes, hello. For those who don't know me, I am Peter's PhD student. I'm a third year at Sydney Uni, also Ben's PhD student. But I'm based at Sydney Uni, not UQ with Ben. Yeah, and I've been leading the development of dLux during my PhD, which is essentially a differentiable optical modeling software, which is a bit of a sort of reframing of the way that typical problems are approached in optics. And it's been so far very, very useful, very handy. I'm sure Peter's given a very brief intro, but yeah, so if you do work with optical software, dLux is sort of in a similar vein to Poppy or HCI Pi or Prism, if you've used any of those. But the key difference is that dLux is differentiable, which is to say it's built in a machine learning framework and is able to take advantage of autodiff. So if you're unfamiliar with autodiff, it's essentially the key piece of mathematics that allows for machine learning to really be possible. And it's the key part of it is it lets the computer take the derivatives through your model for you, and your complexity of that of those gradient evaluations for each parameter scales with the complexity of the model, not with the number of parameters you're taking gradients with respect to, which is how you can optimize billion parameter models in machine learning. So that's beneficial for us because it lets us reframe the way most problems we tackle. Yeah, it reframes most of those problems from being an inverse problem to a forwards model problem, where if we can now, if we have some optical system and we want to understand it, we can just forwards model the physics and then gradient descent recovery the actual physical parameters of the model itself. So this is actually a really, really beneficial way to explore optical systems. It's a lot simpler in how you can approach things, and it's really principled. So that's sort of the elevator pitch. A bit more details. So we use JAX as our machine learning framework, which, if you're unfamiliar with that, some of the other ones that are common in the field are PyTorch, and historically Theano, I think, was another big one that was used in the field. But JAX is Google's latest machine learning library, and the sort of key points about JAX is that it's a NumPy-like API, which most people are very familiar with. So it's pretty much all in Python and NumPy-esque sort of syntax, which is really nice. It's not too hard to sort of translate existing NumPy code into JAX. But the other benefits of JAX is that one, it natively runs on GPUs. So you don't have to mess around with trying to write different versions for specific hardware. It has native vectorization and parallelization, so utilizing multi hardware systems is very straightforward. It also has JIT compilation, which is where essentially the first time you run your code, if you compile it, it compiles all of your Python code into XLA. And then that is what is actually evaluated on the hardware, which basically allows it to be really, really fast. And I believe XLA is basically as fast as Fortran at doing matrix multiplication, stuff like that. And they've also done a lot of great work in terms of doing compute graph optimization through their compile process. So the fun thing is you can sort of write a poorly written function and a well-written function. And even though in Python side, one will run much slower than the other, once you compile into XLA, they typically will both run at the same speed. So JAX is a very nice framework to work in. And as well, it also has better support for higher order derivatives, which will be important to some of the stuff I'll talk about shortly. So yeah, that's sort of the brief overview of the context of dLux and what we're trying to do. So yeah, also by the way, if you have any questions, please feel free to just interrupt me or
One quick question. You say it
yeah.
runs on GPUs,
Mhm.
but can it also just run on normal,
Yes.
multi-cluster machines with a switch of some sort? And
Yep.
Yeah. Basically, it runs on all hardware, sort of with very little, if no configuration. If it detects a GPU device, it'll run on that. If it detects CPU device, it'll run on that, or you can select which one if you have access to both.
Right.
Yeah, so Google does a lot of the hard work in terms of making it run fast and all the different hardware. So we get to focus on writing the fun bit, which is the physics and the optics. Yeah, so I guess I can just take you through some of the cool results that we've been doing with this. So the first I think a nice illustrative example in terms of all of this stuff I'll show you. So this is essentially a we're running a forwards model of a Tolman-like optical system. I'm going to assume Peter has given you brief context about Tolman and the how we sort of built the world's worst telescope for anything other than constraining the binary star separation because we have a funky PSF that looks something like this. Um, uh, yeah, and so I'm just using that optical system here as the framework for a deconvolution problem. So essentially, we're just starting out with a normal Tolman PSF, and then we're adding optical aberrations to that, which is why this PSF over here looks funky. And then we're testing out deconvolving just an MNIST image, sorry, an MNIST digit. So just this one over here. Just as a sort of example test case. This is not meant to be astrophysical. This is more just a demonstrator that you can do joint phase retrieval and deconvolution. So yeah, so you take your PSF like this, and you can build it with.
MNIST is a handwriting sample that's commonly
Oh
used
yes.
in learning. So that's the letter O, I don't know, or something.
O D.
The D maybe. Okay,
Good question.
But yeah,
It's the number
yes.
0.
For this purpose, we're not classifying it, so it doesn't matter.
Yeah, sorry.
No, please do. Yeah, so you basically take your point your point source PSF, we get the distribution and we convolve it, add some noise, and you get a PSF like this. And what we're going to try and do is start from a naive understanding of the optical system. So we're going to start with a no resolved component, and with no aberrations on our optical system. And we can essentially just forwards model this and directly recover both the phases on the mirror as well as the distribution of the resolved component. So you can just jointly recover those at the same time. So yeah, this is what we're covering from. And you just do some very straightforward gradient descent. And this takes, I think, like 2 seconds or something on my laptop. It's quite straightforward. And you can see we forwards model to this point here. We can see our residuals looking quite good. And you can see that we basically recover the distribution just sort of straight up. This is without any sort of regularization. It is a sort of quite high signal model we put up here because, as I said, this is just a proof of concept. And then so you can see we recover our distribution quite well, considering no regularization. And we can also see that we recover the aberrations on the primary mirror as well, very well. So that's just sort of like yeah, sort of rather than solving the inverse problem, we just forwards model directly what we see. And are able to jointly recover both the state of the system and the astrophysical scene that we're observing, if there were MNIST characters floating in the sky. But yes, a demonstrative example. Yeah, so one of the other benefits of dLux is, as it is built in these machine learning frameworks, is that it natively basically integrates with machine learning models. So one thing we have looked at in the past and are developing further with some other collaborators in Montreal, is using machine learning models as a prior over our resolved component to act as a regularizer in this deconvolution. So we initially did some tests with some normalizing flows, which is part of why we use these MNIST characters, is because it's easy to train a normalizing flow model on these images. And I don't have the notebook up here for it, but for example, we can basically directly plug in that machine learning model as our prior and jointly gradient descent over our astrophysical source and use that machine learning model as our regularizer, which is pretty good. So there's no extra work. It basically all operates as one big system on its own. So that's one of the other major benefits about that is it lets you sort of interface with these two sort of physical models and machine learning models quite seamlessly. So yeah, that's one of the really fun things about it. What else? Okay, so the Tolman pupil, which I'm sure Peter has talked about, that was designed with dLux. So I have this paper here, which is currently, I believe it's past review now, and I think it's just waiting for publication. And so this basically covers, it's not the exact details of how the Tolman pupil was designed, but instead it is just sort of demonstrating how we use dLux to design these kind of things. So we're optimizing over the Fisher information, which so yes, optimizing the Fisher information of a optical system. So if you're unfamiliar with the Fisher information, it's essentially a measure of the lower bound of the variance of your parameters, which is to say, irrespective of how you do your data analysis, your Fisher information tells you what's the best performance you can, or how well can you constrain any one parameter. So yes, the interesting thing about that is you need to calculate the Hessian of your likelihood function to be able to evaluate that. Which, as I mentioned before, JAX is uniquely good at higher order derivatives, which is obviously important in this situation because we want to take a Hessian with respect to our likelihood function. So yes, with this Fisher information, that's only yes, and it's provably only stable. This calculation is only stable through autodiff derivatives. For example, you can't calculate this with finite differences, as it doesn't have the it doesn't converge essentially. So that's one of the cool benefits. So with this Fisher information, that is essentially gives you both the covariance between all of the parameters in your system and the minimum bound, the lower bound on how well you can constrain it, marginalized over the rest of those parameters. So given that we can calculate that then lets us wrap another gradient calculation over the top of that and optimize either the Fisher information matrix itself or specific norms or specific components. So for the Tolman system, this is essentially the approach that we took, where we calculated the Fisher information of over the entire state of our optical system and the state of the binary star system as well. And then we gradient descent such that we minimize the lower bound on the variance of the binary star separation marginalized over the rest of our system. And so, and for reasons, it needs to be a binary mask, which we use a cool climb algorithm that Ben came up with. And you can create these really cool, funky looking patterns like this. So this is an example at the top here of a pupil that we started with. And then after optimization, you end up with the pupil on the bottom, the pupil and PSF pair. So you get these really cool, funky, natural looking PSFs and pupils, and then we can compare them. So these are the marginalized variances of each of our parameters. So the main one we care about here are is our binary star separation. So we're comparing three things here. One is the airy disk, how well like basically a just a normal optical system would perform in this situation. And then we have our initial pupil that we start with, and then our post-optimized pupil. So the key interesting result here is that the final constraint on the binary star separation with our optimized pupil is a factor of 4 to 5 tighter than an airy disk system, which is actually a really interesting result because the airy disk, essentially how well you can constrain the position of a source through an optical system is proportional to the spatial gradients of the PSF. And the airy disk is provably the PSF that has the maximum amount of spatial gradient for a binary valued pupil. But as you can see, yes?
What are the units on the?
Yes, these are arc seconds. For yeah. So there's this is in the paper. There's a sort of detailed in here. What was that? Sorry.
If you go back and look at the picture, it doesn't look like that's the answer. So the bottom one, right? That's your optimized one.
Yep.
It looks like there's a ton of power at. So I think I see what you're saying, right? So you're clearing out the inner hole of 0.5 arc seconds, but then you're creating a lot of power at 1 arc second, essentially.
Yes, that's this. So there's at the back here, I've got a series of other post-optimized pupils. So you see, start with it does tend to concentrate it around a central peak here. But yeah, the general idea is we want to create these two PSFs that sort of have overlapping these overlapping peaks, as that sort of gives us a much a measurement that's much more robust to optical aberrations, because you get this the sort of common mode warping between the two, and so you get a much better metrology between those two stars, because we're making a relative measurement, right? We're essentially measuring pixels on the detector or fringes, so you need to have a very good constraint of the pixel scale and defocus, because if you had those things drifting and they were unconstrained, that measurement would be highly covariant with your binary star separation. Yeah, so coming back to these parameters here, yeah, as these are all sort of on simulations, so the actual values themselves, it's more about the relative value is the important part here. But yeah, as I said, we reach about a constraint of about 4 to 5 times greater than the airy disk, which, despite provably having the maximum amount of spatial gradients, which is proportional to how well you can constrain a source position, essentially the airy disk is really poor, or really it does a really poor job of constraining the wavelength and the pixel scale of the system. And those measurements are highly covariant. So if you want to constrain a single position of a single source, the airy disk is the way to go. But once you want to make like a relative measurement, such as the binary star separation, where you need to basically like measure the distance between two things on a detector, well, then you need to really know your pixel scale very well. And so this pupil that we've designed is essentially able to marginalize over the rest of these parameters of your optical system. So yeah, your binary star parameters, as well as your instrumental parameters. So there's also a whole series of Zernikeys that have been marginalized over here, but not plotted, just because the results aren't that interesting, and it doesn't really sort of add any new information. But yes, there are more parameters that are marginalized over the system here. And yeah, we tend to show that despite the airy disk being sort of what might be the sort of reasonable idea of what is optimal, we can design a far better pupil with dLux using these very principled methods.
So how do you deal with, the full breadth of whatever your filter passband is? I mean, the air disk is at one wavelength, and obviously you maybe have a factor of, R of 2 or 3 resolution, so a broad wavelength range.
Yeah, so we just model the whole wavelength range directly. So this is all chromatic modeling.
Okay, so when you say an airy disk, it's some fiducial airy disk,
Yes.
which incorporates the whole 4,000 angstroms to 8,000 or whatever your coverage is.
Yes, yeah. So we're just taking a sort of,
Yes,
when I
yes,
say
yes.
airy disk, I more mean just a sort of empty pupil optical system. So in this analysis, this is with the secondary obscuration of the spider. It's not a perfect airy disk, but just a sort of empty or filled pupil, whichever way you want to refer to it, modeled over the full wavelength range of Tolman. Yeah, so yeah, that's sort of part of the benefit of this. You just forwards model the whole thing, and it kind of like encapsulates all of that in it directly. So yeah, so these are some things that sort of just wouldn't be possible in conventional optical modeling frameworks, and we can sort of do this very principled way of designing instruments and components of instruments to basically maximize the information about whatever scientific variable you may care about. So yeah, that's one of the really cool things about it. All right, what else should we touch into?
To Kevin's point, this can't possibly work over 4,000 to 8,000 angstroms, right? It has to be over.
It's it's over the Tolman band, which is 110 nanometers, 120 nanometers, Louis.
Roughly, yeah, roughly that.
It is.
Okay, fine.
But it's polychromatic. It's a polychromatic simulation. It's 500 to 600 nanometers roughly, but the simulation is fully polychromatic. So yeah, Chaz has a point. It's not actually an airy disk. It's just the PSF of an open pupil over that polychromatic band. But yeah, it's really remarkable. You're not used to even understanding what you're looking at here, because this is performing an optimization of components in your pupil or in your apparatus, and following those derivatives down with respect to this very abstract Fisher information of a binary star recovered at the end of a long sequence of otherwise difficult to perform operations. So you're optimizing your apparatus. This is I guess differential design. Do you have a name for this, Louis?
Informational design? I don't know. Naming things is Ben's category.
Driven by the fact that you can model it so fast that you can optimize with respect to very abstract quantities.
Yeah, I mean, I guess one question I had then is, this is optimized, say, for alpha cent. That's fine. Let's say I want to optimize this not just for one star, but let's say I want to do a dozen stars. To what extent is it so heavily optimized for one system that it is significantly not well optimized for any other system?
Well, the good thing about Tolman is that Tolman is only optimized for one system.
Yeah.
But in terms of other systems, so one of the things I'm really interested in is coronagraph design, to be resistant, for example, to low order wavefront error and all that sort of stuff. In which case, what you would want to do is to optimize the sort of the average performance over an ensemble of cases.
Right.
There's no reason you can't do that. So this is
That's what I was asking. So I could input, not just alpha cent, but a dozen systems and say, give me, the best pupil that does the best job for 10 different systems.
Louis already done that in a different regard. This is already optimized over a whole ensemble of potential bends and warps to the primary mirror. So he's got a whole set of Zernike's that he throws in and said, we don't know how it's going to be bent and distorted, but it could come from this massive set of possible bends and distortions. Find me the best pupil design to recover a binary star, given the fact that my telescope is made of rubber and it could be bent in a number of ways. So it's already doing that.
What about the opposite of having the pupil that's set, but then you deform the mirror according to the optimal?
I think any of these are possible. Yeah, these are all.
I mean, we're kind of planning on doing that with Tolman a bit. We're going to be running a real-time forwards model on the satellite hardware, and using that partly to inform the tip tilt system to try and keep the pointing more stable. So yeah, that's sort of just the low order Zernike's, but yeah, the same concept essentially. Yeah.
So
one question I had is, this pupil looks dramatically different, Peter, than the very nice little trefoil shaped things that that I'd seen for Taliban, over many, many years.
Yeah, well, we could go into that. There's basically the final chosen design is equally good in these metrics. So basically Louis found dozens, in fact, of solutions, all of which bottomed out at the same information theoretic level, and we got to choose among a whole host of patterns. But you're quite right, a lot of these ones descend to a somewhat different looking, more broken version. But we can come to that later, perhaps.
I mean, yours look like Picasso, and these look like, I'm not sure who.
You might be unsurprised that aesthetics actually came into it in the end, and we chose the one that looked prettiest in the end because they were I know, like, Louis, I don't like that one. Can you give me another
Yeah.
one?
They all looked they were all performing about the same, so we went on the coolest
They
looking
look like
one.
something that that you'd see in a lava lamp or something.
Best on the
I'm
mission.
glad you like our style.
Oh, did you have a question?
I did, going back to the question about how finely tuned this is for the alpha send system, what is the sort of range of systems that you could potentially use for one setup? So it's tuned for a binary separation of 10 sharp seconds, but
Yeah, I mean, that's not really a dLux question. That's a sort of a more a Tolman question. I mean, dLux is a generic optical modeling package, and maybe we should move soon to web examples.
Yeah.
Tolman itself, that architecture. Actually, maybe ask me that afterwards. I think we'll stay on dLux for now. Is that okay with everyone? Because that's a Tolman specific. Yeah. Look, take it away with where you were going next, or Ben.
Yeah. Ben, did you want to say some other high level stuff?
So like just sort of at a high level, right? This is a drop-in replacement, in some sense for something like Poppy or, an optical Ford's model package like WebPSF, but is used to be a replacement for data reduction itself. Instead, you actually Ford's model all the way to what happens on the pixels when you've got science data. And then a lot of the projects we're working on at the moment, it's about using the possibility of doing high dimensional optimization to fit a physical model, not a machine learning model, a physical model end to end to these data to calibrate all sorts of systematics. And so, I mean, I think the thing I'm most excited about is the stuff that Louis has been working on with us at the moment on James Webb. So, do you have any slides on this, Louis, or do we want to just?
Yeah. I can sort of.
At a high level, are you guys all familiar with James Webb aperture masking interferometer?
Yeah, people have.
Yeah. So the long story short is that, like, asterisk, it doesn't work in the sense that it's very severely limited by the brighter fatter effect in the detector, such that the visibilities that you get out of this aperture mask do not calibrate well. And so this has been vexing us for a while. And the sort of the spoilers I'm going to give for Louis' talk is that if you Ford's model the entire instrument end to end and learn all of the optical aberrations through AMI, all the slight misalignment of the AMI mask, and a neural network-based model for the brighter fatter effect, AMI works. And so I was a little bit gutted to get James Webb Cycle 3 notifications this morning, including one saying, oh, this is a great proposal to use AMI, but it doesn't work. Everybody knows that you can't get 0.1% visibilities. I thought, damn, I wish this paper had been out before Cycle 3 analysis, because yes, we can.
Yeah.
Is the spoiler there. And so at a high level, I recognize that AMI is slightly niche science, so I think there are a lot of things that are going to be really good with AMI. So I'm really excited about doing debris disks. I'm really excited about doing AGN close environments, but it's a really good test case for what I think is a little bit more nature paper science of, for example, the NearCam high resolution imaging modes and the NearCam coronographic mode in particular. Calibrating the hell out of those, which again hasn't really been achieved so far with kernel phase analysis or similar alternatives, is, I think, pretty realistic given what we've been able to do with AMI. And so at a high level, I think that's the pitch here, is that using this differentiable Ford's model you can do things that machine learning couldn't, and that classical data reduction based on Fourier methods and so forth couldn't, because you forwards model all the way to ramp level data. You run it on, very, very fast simulation at very high dimensions, and remarkably it works.
Do you have
And so
the joint recovery of the mirror phase errors together with the BFE, together with the background?
I think it's certainly got some notebooks showing that.
Yeah. I can come to that. Yeah. So yeah, as Ben Pierce said, the main place we're applying this now is the interferometer on James Webb. And the brighter fatter effect just kind of murders your visibilities. And so all the results coming out of AMI have been sort of well below the sort of expected performance out of the system. So yeah, we decided to try and tackle that with dLux. And there's been some sort of very fun and interesting results along the way, particularly for actually like calibrating the instrument from on-sky data. Which, you can't go up and measure anything on Webb anymore. It's gone. But the PSF encodes that information about your optical system anyway. So when we started tackling this problem, we built dLux Webb PSF, which is essentially at points has been a machine precision match to Webb PSF for optical modeling, but differentiable, obviously. And so we started there and then started applying that to the AMI data that we had. And it was really interesting because we kept seeing this same characteristic residual all across. I'm not sure, sometimes the colors don't come across very well on Zoom, but you can kind of see there's sort of like a blue ring here and like a red ring here, and it kind of alternates. It's this sort of sync pattern that's overlaid on top. And it took us a while to figure out, but we realized this is actually a miscalibration of the aperture mask hole size. So basically the face-to-face measurement of these hexagons here. So Peter was one of the commissioners of this instrument, and we figured the mask was something that was static and known. But somewhere along the way, there was a decision between a face-to-face value of 0.82 and 0.80 meters, I think. Projected onto the primary. Obviously, it's actually very small. But yes, so there was essentially somewhere along the way there was a mix-up where the manufacturers got the correct value of 0.80, and Webb PSF, I think, was not updated with this new mask hole size, and so it uses this 0.82. And so we kept seeing this residual, and we sort of couldn't figure out for a while. And so we decided, okay, let's just try and infer the mask directly. We'll just say we don't know what's going on and try and recover it. And essentially, we just gradient descented that on the data, and it just kept spitting out this 0.80 value. And Peter kind of went back and had a look and realized, oh, that was the actual value that we went and got manufactured. So that was pretty fun to be able to basically calibrate, the aperture mask of James Webb at L2 from directly from data. So that was a really sort of fun task. You can see it kind of pushes the residual way back down, and you lose that structure. That's one of the other real benefits of these sort of really physics-informed forwards models, or physics-based forwards models, is if you're
Yeah. No, 0.82 is in all the documentations. It's in Webb PSF. It's baked in everywhere. And I looked at my notes and there was 0.80, and I'd never, so don't know where that 0.2 came from, 0.02. But it's also, it's a pretty small fraction of the mask size. So,
So that's really one of the benefits of these physical forwards models. Is we tried many different things to try and account for this residual that we're seeing. So we're trying like Fresnel propagation, intermediate planes, like a whole bunch of different things, and then the magic is once you find the right thing, you just crash through, and you're just like, oh well, that was it, cool, easy, simple. So it really lets you probe the physics in a real sort of direct way, and understands your system sort of at the whatever is setting your limit on your precision or your results, your residual at any one time. You pretty much just cycle through different options until you find the one that recovers it, and you're like, oh, okay, well, there you go. And yeah, we've had some nice verification with this one in particular that yeah, that was actually the correct value after all.
So
So
just looking at the residuals, okay,
yes.
so yeah, I was just gonna ask, it looks like you go ahead one slide and all of a sudden things get magically better.
Yes. Yes. That's because yeah, so these results are actually from like 4 months ago, like right when we started on this project. So there's a lot of other sort of details about data processing. And so for example, here you can see the central part is NAND out, and that's sort of our way to try and make the brighter fatter effect more linear, because the dynamic range is much more consistent over the outer wings and in the central peak.
Do you want to show the slides, sorry, the notebook where you actually have the recent residuals with the BFE model?
Yes, let me show.
These residuals are much better than you would get normally, but the residuals Louis has been showing me over the last couple of days on the like work in progress version, it's not there yet.
Yeah.
But it's there, you know, in the sense that they look a lot better.
Yes, let me. This is now where, sorry, I might just zoom in on one of these. Yeah, so this is now what our residuals are looking a lot more like. So this is sort of bit down, but we sort of ended up using a convolutional neural network to do this brighter fatter effect modeling.
So the BFE is the reason the residuals weren't good. So the
Yes.
main, after getting the mask hole size right, the next problem was the BFE.
Yeah. So yeah, we sort of do our whole own different type of data processing, doing up the ramp modeling rather than the sort of default output. Actually, let me just jump back quickly just to give the context. Oh, that's the same one. Yeah. So the as I was saying, the brighter fatter effect, you can see that these residuals, like in all of the peaks of the normal MEPSF, which was click back to here, you can kind of see it's got a series of quite structured peaks. And then if we come back to here, we can see that it's overestimating the brightness in the peaks and underestimating the flux in the surrounding peaks. That's just the combination of jitter and charge bleeding effects. And yeah, essentially it kind of just it ruins your interferometric information. So the first thing that we tried to do was we built a non-linear polynomial based convolution, essentially, to try and be able to account for this effect. And we were able to get much better. So in the well sampled data, so the 4.8 micron and 4.3 micron data, this is a pretty good solution, and it gets you like quite far. As you can see on some of these residuals here, but it ultimately doesn't take you far enough, because some of the data is below Nyquist sampled, in particularly the 3.8 micron, the 3.8 micron filter, which means that you basically need to work in the oversampled PSF, because the curvature over a single pixel is quite large. But unfortunately, that polynomial convolution doesn't scale very well for reasons that I won't get into. And so we decided to basically try out a more machine learning based approach, and basically use a convolutional neural network to predict this charge bleeding from the oversampled PSF. And it has been basically showing really fantastic results. And so this is essentially you build this convolutional neural network, and you're not training this on its own in a conventional machine learning sense. We're essentially taking that and putting that in the forwards model of our system, and then jointly training the entire optical system, as well as these detector parameters, while recovering the state of the mirror phases and, for example, positions and brightnesses of various stars that you're observing. And so the sort of the machine learning model, the convolutional neural network, just sits in there and gets jointly trained with this forwards model, and you can construct it in such a way that it only has enough rope to you know, push around charge in a conserved way, so that it actually doesn't have the ability to overfit, right? You know, you'd think conventionally, if you threw a machine learning model into something like this, it would just fit everything out, and you just, okay, well, it's over constrained. You need to spend a lot of time, you know, trying to build sets and yada yada yada. But we can actually train this directly on the data, because it's constructed in such a way that it doesn't have that leeway, and it will just hit the noise floor, and we'll be unable to do anything with that noise, because that's not something that the model's been constructed to do. So it's this sort of, you know, reframing of the way you even approach these problems, and you can have this direct integration of machine learning into your systems, which is which is really fantastic. So to give you an idea, what we're trying to do essentially is we're trying to train what we are calling a reference model. Which is essentially we're taking trying to find every point source that's ever been observed by the interferometer on James Webb, and we're using that to calibrate both the detector effects as well as the aperture mask, because we believe there are small shears and rotations to do with how the mask was put in the pupil wheel, and so that means we need to jointly optimize our optical system over a whole bunch of different data sets together, which is something that is very possible, and we've been doing. So these figures aren't the nicest thing in the world, but it'll give you kind of an idea of the kind of models we're working with. So I think this is fitting 6 different data sets simultaneously, just as an example, training our nonlinear convolutional brighter fatter effect model. And so you can see we're covering the individual positions of each star, the aberrations on the mirrors for each individual observation, the brightnesses of each star. So those are all fit on each individual exposure. And then we can jointly train the brighter fatter effect convolutional coefficients at the same time, as well as recovering the deviations in the positions of the aperture mask holes, the size of the aperture mask holes, the rotation and shears and compressions that are applied to it, as well as other noise parameters in the data as well. And this is all stuff that I can run on my laptop. I think the most I was able to push it to fitting, I think it was 96 different individual exposures at the same time on my laptop, calibrating all of this, the whole instruments, detector effects, aperture mask, as well as actually extracting the data from extract the information from the data. So it's very powerful, very principled. And you can just sort of, here's a brief overview of kind of what these residuals look like, more or less. Now there are sort of small details in this, in terms of we have to do our own unique way of data processing. So we take the outputs from a slightly modified version of the stage 1 pipeline from James Webb. And basically the last step they do in the pipeline of stage 1 is they take the up the ramp reading, and they fit a slope to it, and then that's your brightness value for that pixel. However, if you have charge bleeding into a neighboring pixel or from a neighboring pixel, those ramps are no longer straight lines. They're curved, right? And so it's going to inherently, if you try and fit a straight line to that and fit to what's the outcome of that, you're inherently going to have tangled in this charge bleeding effect into your PSF in a way that you can't necessarily model. So instead, we basically just work with that ramp level data. So we model our PSF and model all those realizations up the ramp, and fit that all at the same time, so that we're not building in these sort of where we can detangle these effects directly, and then that's basically kind of getting us where we are to now. And I'll just sort of jump to these figures here. So the other main interferometric fitting pipeline is called Amical, and ours is called Amigo. And so already, I mean, this was, the development of this started in like November, I think, or maybe late October. I hadn't worked with interferometric data before that. So yeah, and there's sort of a few other pipelines, and they all kind of hit a similar flaw, using various different techniques, of similar to the Amical limit here. And yeah, you can see with Amigo, we're able to push the contrast limit by two and a bit magnitudes. And as well, this is also just our preliminary fitting. This is all without polynomial convolution, nonlinear convolution, rather than our sort of more present convolutional neural network solutions. So already, despite this still very much being in active development, we're able to push the information you can get out of this data by quite a significant amount. So yeah, that's essentially where we're up to on all the AMI stuff, and kind of give you an idea of the different types of calibration and possibilities, and yeah, sort of overview of what we've been doing.
Just Louis, quickly, where were those contrast curves with respect to the forecast that we all optimistically applied for time for? So the problem was that yeah, I know, but when we write proposals, we were saying Webb gets to this much on this star with this much integration. We had all this calibrated and ready to go, and then we hit this purple curve, which is from the old Sydney Amical code. And this is, well, also let me add, this problem isn't only applying to the interferometer, right? So the kernel phase people and all the people digging stuff out of PSF cores have hit the same BFE walls. So Louis, is that, are we there yet? Where are we with respect to Kramer-Rao on this?
I don't think we're quite at Kramer-Rao level, but we are approaching, dare I say, asymptoting towards it.
Yeah, I think we're actually not completely sure yet, because it's about how we normalize the likelihood function. You know, it comes down to like the read noise. I think that calculation's not there yet, but I actually think it's pretty good.
Yeah.
Yeah.
We've already been able to push out detections far greater than other pipelines have. So already where we are is a you know, doing quite well and improving, and it's sort of, we're just building on from there. But yeah, this is all new code from like November.
A little conscious of time. Do we want to try and give Max a crack at MIRI data with the volcanoes or something? Or Ben, did you have another plan?
Well, I thought probably the best thing to do is to actually talk to our Pasadena colleagues about what do you guys sort of see as interesting here, and what's sort of your use cases for this. And yeah, also just to flag, as one of the things we can talk about is image deconvolution. Because this model is differentiable, we can simultaneously, in a principled way, infer the PSF and a scene observed with that PSF. And so Max has got a you know, crack at some existing data with sort of current generation regularized maximum likelihood methods that works pretty well. But we're also working with the people in Montreal to use machine learning to improve the scene reconstruction given the PSF inference. And so I think there's a lot of potential there.
Yeah, well, certainly, you know, the stuff we're doing with NERCAM,
Hmm.
you know, we've got, you know, 2 papers out, where it'd be interesting, you know, to see how applying these techniques would you know, enable us to push a bit further.
Which
I mean,
papers do you mean? Is this
there's Fomalhaut.
Yeah.
You know, is there, so that's 444 and 356. We're just finishing HR 8799. That's just in review right now.
This is chronographic?
Yeah. And then also EPSARI. You know, and all of those are ones where, you know, those are 3 of our sort of chronographic moonshot programs, where it's either 444 and 356 or 444 and 210. Where, you know, we're doing pretty conventional ADI plus RDI, trying to, you know, push in as hard as we can. So those are pretty good test cases for, you know, what one might be able, you know, to see what sort of, at least from an injection recovery standpoint, could we do better. with some of these things. You know, particularly in close, we have both subarray data and full frame array, you know, to work with. I don't think Jorge is not on, unfortunately, but Jorge, who's former postdoc with Dimitri and myself, now up at JPL, Marie Goof, Jeff Bryden, and I have all been working on that. And I think those are data sets would be immediately amenable to, you know, jumping in and seeing what could be done. The 8799 data are actually public at this point, so one could just jump in and start working on them. One of the things we have done that would be a useful starting point potentially is the NIRCam data take quite a lot of cleaning up, you know, in terms of hot pixels and so on, particularly since these stars are so bright. We only get a few samples up the ramp, so it's a bit challenging. But, you know, we have the data that have been cleaned up from that standpoint, and some stripe removal has been done. So you could sort of give you some data at some intermediate level and, you know, just see, you know, how some of these techniques would work on those data where, you know, we've milked it as hard as we can, but, you know, another factor of a magnitude would be fabulous.
So I think, yeah, no, that's what we want to do basically. And I think we're not ready to just
Okay.
yet. There are two reasons. One is non-trivial and one is labor intensive but easy. And one of them is we haven't got a solution, but it's probably fine. And so the problems there are, one, we need to code up a model of the coronagraphs. And so that's labor intensive but easy in some sense. Just get it going. We need to get a calibration data set like we've got for AMI, and then, you know, infer all the very small alignment details of the chronographic occulters and Leo stop and that stuff. I think that's pretty doable. We need, you know, labor power in order to do that.
Right. So what, just to mention on that, I mean, the person who designed all that stuff is John Christ.
Yeah.
And he's still available. And if you needed to get a ZMAX model or, you know, anything like that, you know, to help, we could get John to provide that.
Yeah, I mean, I think really we're just bottlenecked by we don't have enough students and postdocs on the project.
Right.
You know, if anyone can help us just put this together. The other thing is that the Amigo model, as we're calling it for AMI, is not performing. So it's performing very well on high group count data, and it's performing only moderately well on very low group count data. There's a couple of these stars are very bright. You're going to get 2 or 3 groups up the ramp, and it's still better than the existing state of the art, but not nearly by the same extent. I think
And that's been our problem.
Yeah, I think partly that's about all of this sort of like striping effect, as you see, is the main residual in Louis' images that he was sharing. You know, stuff like that. You know, the brighter, fatter effect, you get less grab on it if you've got fewer groups to watch, basically to watch the bleeding happening. And I think that's doable. I think there is no principled reason why we can't get it to work. It's just we haven't got it to do so yet. But so
the other sample that might be better from that standpoint is Josh Schleider has been doing a group of M stars, and they're just fainter to begin with. I mean, we're not talking magnitude 1 stars with names like Vega or Fomalhaut, but sort of anonymous, you know, M stars where you probably do get more groups. That particular program did not have individual reference stars for each M star, but rather it was a self-referenced survey. But, you know, again, I think Josh would probably be, you know, more than willing to put some of those data either in the public domain already, or, you know, could certainly make them available.
Yeah.
And those would be 2 good NIRCam samples to work with.
You don't have a keen
Does it?
student send to Sydney maybe, or Brisbane?
Excuse me?
You don't have a keen student to send to Sydney or Brisbane, or a postdoc or something?
Or someone in Caltech who's willing to, basically there's about 1 to 2 months worth of work. to get coronagraphic data into the same format that we've, and volume that we've been training the AMI model on, and, to code up the coronagraph model. It's not tons of work, but we're just bottlenecked by that, really. We've only got one Louis, and we've got a couple of other students who are working on other things like Max on deconvolution, which is again going to be relevant. I've been talking to Max Miller-Blanchard about trying to look at like discs with the chronograph that are close to the inner angle, where I'm pretty sure this is really going to be the only method to deconvolve those. But
right. So what we could do, I mean, I'm glad actually we've recorded this, because I think, Lynn and I, both know that there's some students, certainly in Dimitri's group who might be interested, or postdocs, who might find this interesting. I'm working with a student, Aniket, who Peter, I think, introduced himself to you. He's on a slightly different project right now, but this is something that he or one or two of the other people working with Dimitri might be interested in. So I think, Peter, you send me the link.
I think he was going to be here, but I think he had a clash with.
Yeah, he had classes until 5, unfortunately. But
we've worked with Yenzi Shin from Dimitri's group before in terms of students.
Yinzi's online, or she was before.
Yeah, Yenzi was on.
Yeah, Max, if you've got a few minutes, can I invite you to have a crack at showing what you've been doing with Miri? It's work in progress, but it's really cool.
Yeah, sure. It's definitely very early stages, so nothing quite as exciting as what Louis showed you.
Miri or Io?
Io, yeah, wasn't it Miri?
Oh,
Yeah,
Io is
no.
Io is AMI, but we've also got Max's work on Miri stuff.
Oh, sorry. No, yeah, no, it was AMI. Of course, it was AMI.
Yeah, Io is a little bit more exciting.
Io, yeah.
So it's in the similar vein as what Louis was showing earlier with those image deconvolution of the MNIST digits.
And
so
that combined with Amigo.
yeah, combined with the model of Amigo building. So I don't know why or when, but for some reason there exists aperture masking data of Io, the moon of Jupiter, and so we're figuring, oh, if there's data there, we might as well do something with it. And it's not a massive science opportunity because we have spacecraft over at Jupiter already, but we can still try and test out A, how well our pipeline's working, and B, how well this image deconvolution method is going to be. So at the moment, it's still I can tell there's a lot more work to do to get it to its potential, but like even just initially you can see I'll just show you an image, just sort of like kind of where we're at. So this is an image that I've recovered. So basically it just like it takes some source like as in just like an array of intensity values, and we literally just gradient descent on the values of each pixel in that array, simultaneously as gradient descenting on like the positions and the Zernike aberrations and the flux. And because dLux is so fast, we can just do all of this. And so you can see that it's resolving, or maybe not resolving, but you can see there's clearly volcanoes on the surface, which I think is very cool.
Oh, fantastic.
Is this regularized at all?
This is not
whose
regularized
data
at
this is,
all.
we're happy to work with. I mean, we don't want to get into volcanology on Io, so Louis, sorry, you have the kind of the best effort other alternative image that, because I don't think anybody else has got anything but a fuzzy blob out of this. Is that did we have that one in the show? No.
Yeah, I don't. I'd have to look it up. I think there was some. Do you mean from James Webb data or just generally?
From these data, wasn't there
I haven't actually seen any other developed images of this data.
Yeah, I think the Montreal people had some, but I don't know
think
if
I've
they
seen
ever
them.
sent it.
Well, yeah, there were all the attempts that we had with Maxent before you had the BFE model, but
yeah.
Of course.
Yeah, so at the moment, like there's still more improvement to go with the BFE model. But I think also like a big step will be adding regularization to
Yeah, this is not it. This is just a first really rough cut.
yeah.
This is not regularized. This is not with our fanciest model. This is just stick it into dLux.
Yeah.
Yeah, and there's still that hard edge around it, which is baked in because I initialized it prior that it would be like a flat disk, and it hasn't been run for long enough to
Well, we know it
get
has
rid
a
of that,
hard
but
edge, it's fine. But yeah,
maybe not that hard, but it's yeah.
that's
There's more to do, but it looks cool so far. Yeah.
Oh, yeah, that's lovely. So that's 444 AMI.
Yeah, this AMI with the I think it was 430, 4.3 microns.
Okay.
Yeah.
Okay.
But yeah.
Yeah. Thanks, Max. Back to you, maybe, Ben. Did you have any? Wonder whether we need to wrap a little bit here because we.
I think we're probably running up to the time, but look, I hope this is interesting to you guys.
Oh, yeah, no, it's really quite an, just a super impressive thing. I mean, again, we're sort of have the same manpower problems.
Yeah.
But, I can certainly talk with Dimitri, and I think, having, the record of this, to show to have some of Dimitri's students take a look at it, might be an interesting way to see if we can get somebody who wants to, jump in. And certainly we have a couple of data sets for which this could be quite useful.
Sounds pretty
Like
good
I
to
say, one of the M stars, which would have more groups to play with, or, the Vega Fomalhaut crowd, which are, we sort of hit the stops with the kind of stuff that we're doing, which is pretty straightforward. And for example, we don't have any BFE corrections in here yet.
So the things that would help us get that off the ground would be the most accurate understanding of the chronograph, optical configuration possible.
Mm-hmm.
And also, I mean, we're not going to do like a ray tracing simulation. This is purely, physical optics, like Fourier propagation stuff. So, we don't need every intervening mirror. We just need, what the pupils and focal planes look like, basically. And any out of focus stuff we can try and deal with Fresnel. And also, probably more important than that, because we can learn that, a list of all of the PSF reference stars that, are reasonably vetted single star objects. That we can use to build this sort of calibration data set for a reference model as we're doing with AMI. And then I think we should be able to do, pretty easy self-referenced chronographic sort of, PSF modeling.
Mm-hmm.
So that could be good.
Yeah.
And, the other thing I just wanted to really re-stress to bear in mind is this is both a data analysis solution and a, instrument design solution. And so,
Right.
in the sense that if you can forward model what your data look like, you can either optimize the design to make the data look better, or given real data, optimize the design to better match the data that you have. And
Right.
so this is like a nice sort of double thing. If you build your instrument model to design your instrument, then you also have your analysis pipeline for free.
Yeah, I mean, the other thing that this obviously has power for going forward is the chronograph on Roman with CGI. Which I think, will actually be a much more optimized chronographic capability than what we have on web, because it's really designed to be a full active chronographic system. I mean, there may be some challenges with giving you as much detailed information on the chronograph as one would like, because it's ITAR.
So, I mean, one thing about that, just to like put something out there, is that Louis is about to finish his PhD, and the arc over the next 12 months is going to be that we're going to do AMI, and then we're going to try and build the near-cam chronograph model and use it. And that's basically what we've got planned for the next 12 months. there is every possibility that there will be an available person who can drive this for a Roman chronograph, should he have the appropriate clearances.
Yeah, well, can he just come and live in the US for a while?
Very possibly.
I mean, it's still an issue. It'd just still be a foreign national, but those sorts of things become more possible, particularly, if you're looking for a postdoc position somewhere.
Yeah, it's definitely starting to think about that now.
Max has got a couple of years ahead of him before then, but may be in a similar position. So
Yeah, I mean, it's just super impressive.
Yeah, thanks for the tour.
Let's speak as
I mean, I can stop the recording. Let me do that for a start. The bloody thing works. Used to